All right, so welcome to our last discussion on the power method. Okay, so all right, this video I'll take you through what we call the shifted power method. Okay, all right. If you have not subscribed to the channel, kindly subscribe. Okay. Now the power method or the shifted power method is used to compute the eigenvalue which is farthest or nearest to a given scalar k given a matrix A. Okay, so if I have a matrix A, okay, equals something something, I don't know, then if I want to find the eigenvalue which is farther away from certain scalar, let's say k equals 1, okay, which eigenvalue is farther from it, or which eigenvalue is nearest to it. Okay, I hope you understand this. Okay, so let's go through how to find the farthest and how to find the nearest. Now if you want to find the eigenvalue farthest from a scalar k, okay, if you want to do that, then first of all we say calculate what we call the matrix A minus ki. So you have your matrix A, so you calculate for A minus ki, okay, and that will give you a new matrix. Let's call that one B, okay, and apply the power method on this B. So whatever result you get, you apply the power method on it, okay, on this one. So after applying the power method on this, you can get, or you will get, a largest eigenvalue which is lambda n. Let that lambda n be the eigenvalue of largest modulus from this point 2. Then the eigenvalue which is farthest from the constant k or the scalar k is given by this lambda n here, okay, lambda n plus the constant k. I hope you can see what we just did. So simply everything is basically about a power method. So if you really understand the power method, the shifted power method is very easier. So first of all, you find, if you've been given what you call a scalar, and you want to find the eigenvalue which is farthest from that scalar from a matrix, then it means that what you have to do is, first of all, find A minus ki, like we said here. You apply the power method on the A minus ki to get your eigenvalue of largest modulus. Then after that, your eigenvalue which is farthest from this scalar k is given by lambda n, which was the eigenvalue of largest modulus from A minus ki plus k. Okay, you sum them. That is all. Now let's go to the, how do you call it, the other one, eigenvalue nearest to a given scalar k. Okay, so you have a scalar k here. I want to find the eigenvalue which is nearest to this, okay, of a matrix, say A. Then first of all, you have to find A minus ki, okay, so let's call this one B, and then you go ahead and find A minus ki or inverse. So find B inverse, okay. When you compute this, you get a value, you get a matrix, okay, and then you apply the power method on this one, okay. You can either use the inverse power method, or you just apply the power method on B. Just apply it on it, okay, like we did in our last discussion. So this is B inverse to obtain lambda n, and this lambda n will be the largest eigenvalue of modulus of A minus ki, which is our B inverse, okay, or inverse, sorry. Now with this, the eigenvalue which is nearest to the scalar k is given by 1 over the lambda n here. This lambda n is from the A minus ki inverse, okay. So if you remember how to find the inverse power method, you know that after everything you reciprocate your eigenvalue to get your smallest eigenvalue of A minus ki only, okay. But if you want to maintain it, then you have to say that the eigenvalue of largest modulus of A minus ki inverse is 1 over lambda n, lambda n rather, okay. The largest eigenvalue, I'm taking that point again, the largest eigenvalue of A minus ki inverse is lambda n, but the smallest eigenvalue of A minus ki only, this part, is equal to 1 over lambda n, okay. So you reciprocate that one, whatever you get for the inverse, you reciprocate it to get your everything back. Okay, so now let's say I have let's go and take an example. This example is very, very short. Okay, so I have my constant or scalar to be 3, and I have for the farthest, we calculated for the eigenvalue of largest modulus, and we had 2.5 for a minus ki. So what will be our eigenvalue, which is farthest from this, is simply equal to the summation of this lambda plus the scalar. Okay, so lambda n for the largest or the largest eigenvalue of modulus from a minus ki is what, 2.5. Then you add it to 3, and this will give me 5.5. So this is the eigenvalue farthest from 3. Okay, after this I'll give you a shortcut. Okay, it will always work. I've not tried where it didn't work, but then if you try and it doesn't work, let me know. Comment on the comment section below. Okay, all right, so for the nearest, what you have to do is find you have this, and this lambda n here is the largest eigenvalue calculated from a minus ki inverse. Okay, so it means that my lambda, which is the, how do you call it, the lambda here, this lambda, which is the eigenvalue which is nearest to scalar k, which is 3, is equal to 1/2 reciprocate this one plus 3, and this will be equal to 3.5. okay, this is very, very easy. So the eigenvalue which is nearest to our constant k is 3.5. okay, now let me add a page and discuss something with you. If you are being given a, okay, let's say you don't know a, you have been given a like that, and you've been given k, let's say equal to 1, and you have been asked to find the eigenvalue which is closest and farthest from this. You can solve for the eigenvalues of a analytically. Okay, you can solve for them analytically. So solve for them, and you know how to go about them, how to find the eigenvalues and eigenvectors. Okay, so basically you can do this very faster than using the power method. So you solve for the eigenvalues of this one, then you actually compare them, which one of them will be farther from k and which one of them will be nearest to k. That is all. I hope you understand this. Let's say I calculated for the eigenvalues of a, and they were, let's say 5, -6, and let's say let me use -7 or -8, and let's say 6. okay, so you draw a number line like that. This is 1, this is my k, 1 is my k. So from 1 you go to, let's say 5, let me say 6 is also here, but -8 is, let's say -2, -4, -6. okay, -6 here, or -8. So it means -8 here is farther from the 1. okay, comparing to the compare the distance between them. Okay, that is one way you can also use the real eigenvector or eigenvalues to solve for this. You don't need to go ahead and use the power method. And there is one more thing I want to say. If you are calculating for the eigenvalue of largest modulus, and let's say sometimes the answer can be negative or positive, but if you don't see any alternating signs in your iterations, then it means that your answer is positive. But then if, let's say, your first iteration you get x1 to be, let's say, -1, then 0, negative, let's say 2, or it can be only -1, then x2 you go ahead and you have something like 2, 1, let's say 3. okay, let's say 2, 1, 3. Then you go to s3, and s3 was also equal to, let's say, -6 point something, then 1, let's say 2, then x3, sorry, this one to negative, then s4 will be give me positive only. It means that, you see, there was a negative in the first iteration, there was positives only, the negative, 2 negatives, the next iteration, all of them positive, the third iteration or the fifth iteration negative. You see, if you see the negative alternating like that, then it means that your eigenvalue is actually a negative answer. Okay, so whatever you get, you negate it. All right, so thank you, and don't forget to subscribe to the channel.